Here's the dump of the final lecture of Unit 2, which is basically a review. And we start by talking about how to identify and what the nodes are, the angular nodes are in the rotational wave function. So the first bit is that you always need to know where your z-axis is. So we're going to start with the z-axis because phi, the variable phi, is associated with the angular momentum about the z-axis. And just to pick an example, we'll start by discussing what the wave function for y10 looks like, the spherical harmonic 10, which you can also write in the bracket notation because there's a one-to-one relationship between the function as a function of theta and phi and the quantum numbers L and m sub z. And so the clean way to identify these things is with the bracket notation for the L and m sub z quantum numbers. And there's always going to be a one-to-one relationship between the quantum numbers, an individual state, and as a consequence an individual wave function which is a solution to the Schrodinger equation, which is an eigenfunction of total energy, the eigenfunction of the Hamiltonian. So that's our bracket 10. And this in turn is going to relate in this case to the total and the z component of the angular momentum, which I'm loosely writing in that bracket as well. And the key here is that m sub z is quite tightly tied to phi, but the total angular momentum is going to tell us about the total number of angular modes. So L is not tied to theta. L has to do with both theta and phi, if you will. It has to do with the total angular behavior of the system, whereas the m sub z quantum number has quite specifically to do with z. Specifically, the total number of nodes, which is in the z case, so the phi solution is pretty much always slinky. It's always e to the im phi. And quite simply, the number of cycles in slinky is the absolute value of m sub z. So the absolute value of the z component of the angular momentum quantum number, m sub z, is going to tell you how many cycles slinky goes through. And that, in turn, is what we call nodes when we're talking about the phi coordinate. And then the total is given by L. And so, as a consequence, the number of theta nodes has to be the quantum number L minus the absolute value m sub z. So it's the residual that goes into theta. So in this case, because L is 1 and m sub z is 0, the total number of cycles in phi is 0, the total number of phi nodes is 0. There has to be one total node from L, and the only place left to put it is theta. So there's going to be one theta node. Now if there's one theta node, symmetry demands that it be in the middle of the theta coordinate. And the other thing about that z-axis is we know that theta has to go from 0 to pi. So theta sweeps down from the north pole to the south pole, basically. It gives you the latitude. It's actually the co-latitude, technically, because at 0 we're at the north pole. So it sweeps down. And so if there's just one node, it has got to be in the middle. No matter what our space is, if there's one node, it's going to be in the middle of the space. If there's one node in the particle in the box, it's in the middle of the box. If there's one node in the simple harmonic oscillator, it's in the middle of the potential at R equals RE, at the equilibrium bond distance. If there's one node in theta, it's got to be in the middle of the theta coordinate, and the middle of the theta coordinate going from 0 to pi is pi over 2, which is at the equator. So in the case of this system, we draw that node as a dashed line because it's a nodal plane. So we know that. Now the next thing we know is that because there is no z angular momentum, we can have and will have a finite value to the wave function at the pole, at theta equals 0. And that's because that's the only way that you can be at the pole, is to have no z-angular momentum, because the z-angular momentum is associated with the projection, the right angle projection from the z-axis to the sphere that we're, is at distance r, is at the bond, the separation length associated with the rotation in general. But about the z-axis, we have that perpendicular projection, and that distance is 0 at the pole. And so you can't have any moment of inertia about the z-axis if the distance is 0. And so if there is any z-angular momentum, you can't be at the pole. But conversely, if there is no z-angular momentum, then you will have a presence at the pole. The wave function will have finite amplitude at the pole. So we know it's going to have a value up there at the pole, and I have a little green dash. Then we've got our node, and so we make a little bit of we change from green to red at the nodal plane down in the equator, and the wave function is going to basically go from finite down to 0, change sign, turn red, and then go over to become red in the southern hemisphere. So we know that a slice of the wave function is going to look like this. So there's our theta dependence as we go from the North Pole, theta equals 0, down to the equator, have a node at pi over 2, down to the South Pole at theta equals pi. And we're in the negative phase of the wave function. So that's how we dissect it. Then the phi dependence is going to be e to the I m phi, which is e to the I 0 phi, which is just 1. Meaning as we turn around the z-axis and rotate this form that we've generated here through one cycle, 0 to pi over 2 of phi, nothing happens. The function just stays the same. And so this, in fact, is a pz orbital. It just looks exactly like the angular part of a pz orbital. It's got a positive node going up in the z direction. It's got a negative node going down in the negative z direction. So it looks exactly like what you think it should look like. And the actual wave function is the square root of 3 over 4 pi cos theta e to, again, the I 0 phi. If you get a 0 in there, that phi dependence, the slinky part, is just 1. It's just uniform. So we just have a cos theta dependence. At theta equals pi over 2, cos theta goes to 0, so there's our nodal plane. And the actual value of the wave function up at the poles is square root 3 over 4 pi, and that's because if you actually integrate this whole thing using the appropriate integrating factors for spherical coordinates through all of theta from 0 to pi and through phi to 0 to 2 pi, you will in fact get 1 if you integrate the square of this thing, or the complex conjugate of it times itself, which is just the square in this case because it never has any imaginary part, because that slinky part is just 1. Now for completeness, we'll do another one of these. So we'll look at y11. So now we have L equals 1, m sub z equals 1. And the actual wave function here, we're going to start with the normalization. It's square root 3 over 8 pi. 3 over 8 pi, as opposed to the other one. We need our z-axis again. And now, because m sub z is equal to 1, there's going to be one phi node, which means one cycle in slinky. There's one total angular node from L. So the number of theta nodes has to be 0. So that's, again, a quick dissection of the nodes. And now, because the theta nodes are 0, and there is z-angular momentum, the z-angular momentum, the same as the previous discussion, now there cannot be any wave function at the poles. So when theta is equal to 0 and pi, the function has got to go to 0, but that is not a node because it never crosses 0. It just gets to 0 at the limits of theta. So it doesn't count in our actuarial tables for nodes. Getting to 0 isn't enough. You've got to cross it. And so that is not a node, but we know that the wave function will go to 0 at the poles when we're straight up and straight down, when theta is 0 and pi. And that is absolute. Whenever m sub z is not 0, that wave function is going to go to 0 at the poles. There's always going to be a dimple up there. Always, 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 always. You cannot have a finite value, non-zero value of m sub z, and have the wave function have any value other than 0 at the north and south pole. You cannot do it. Okay. Now there's no theta nodes, and so the only option the function has is to be never go through 0. It's going to be all positive, all green in our color scheme here, and so we wind up drawing basically a circle. I'm tilting it a little bit because we're going to need some x and y axes here in a little bit. So it looks like sine theta, and then there's an e to the I phi is the other part of the deal. And so if I draw my y and my x axes here, then the function is this circle is, as we rotate through phi, we're going to go from +1 on the x-axis to +i on the y-axis to -1 on the negative x-axis to -i on the negative y-axis back to plus 1 as phi goes through one full cycle of 2 pi. So that's the one cycle in phi. As we turn around the circle, the amplitude's always 1, or square root 3 over 8 pi, but the complex phase changes. So we go from plus 1 to plus I to minus 1 to minus I back to plus 1. That's a full cycle in phi, and that counts as one node. Another question was asked, what's the Laplacian? Why do we write it that way? And basically the reason we write it that way is that the actual differentiation going on to take a second derivative when you're in spherical coordinates is fairly involved, and the Laplacian just lets us not worry about that. It just says do the right stuff in the right, whatever coordinate system you're in, do what you need to do to find out the second derivative and the curvature, and then you get what you get. So we don't have to worry about the specifics of the operation, because you have to add in multiplying factors and sine squared thetas and 1 over r squareds and all sorts of stuff. That just happens. Just do it, pay attention to what you're supposed to do, and what you get out is the curvature.